Okay, so today we're going to be covering 4 types of reaction mechanisms, that being the Sn1, Sn2, E1, and E2 reaction mechanisms. Okay, getting right into it, we're going to start with the substitution mechanisms, which is your Sn1 and your Sn2. And just a general overview of a substitution reaction. Here you see we start with 3 R groups and an X, and we're reacting with a Z. And for our products, we have basically the X and the Z being switched out. So the X was substituted for the Z. In these reactions, it involves a nucleophile, an electrophile, and a leaving group. And just to cover some vocabulary, first we have a nucleophile. So our nucleophile is our negative or neutral species that has a non-bonding electron. This makes it attracted to positive substances, aka nucleophile. Nucleus would be positive, phile attracted to. This fits in with the definition of our Lewis bases because it has non-bonding electrons. An electrophile is basically the opposite. These are going to be our positively charged substances that are attracted to our negative electrons. And as for our leaving group, this is going to be our group that departs from the starting material, so the group that leaves. And good leaving groups are weak bases. So the weaker the base, the better the leaving group. Here's an example of some leaving groups increasing in strength this way, with OH being the worst leaving group out of this list and OTOS being the best leaving group out of this list. So all of our substitution reactions are going to need a good leaving group for the reaction to proceed. Okay, we're starting with Sn2 reactions. This is a one-step reaction mechanism, and the big idea about Sn2 is that you need a sterically unhindered electrophile. So since it occurs all in one step, we're going to not need a lot of crowding around our electrophile so the reaction can occur. So as you can see from the rate law, the rate of reaction is dependent on both the nucleophile and the electrophile, making it bimolecular, hence the 2 in Sn2. Okay. Some characteristics of the Sn2 reaction: you need a strong nucleophile. When looking at strength of nucleophiles, stronger nucleophiles tend to be negative. Nucleophilicity increases with atom size, so the bigger the atom is, the more it has more ability to overlap with the non-bonding electrons of whatever the nucleophile is trying to react to. And basicity and nucleophilicity are generally parallel. So here I have a list of different nucleophiles in order of increasing nucleophilicity, with H2O being the worst and SH being the best out of this list. Okay. So for our Sn2 reactions, it's sped up by an aprotic solvent. In our product, we have an inversion of stereochemistry. And for our substrates, we want a primary substrate would be ideal, then a secondary, and tertiary for Sn2 proceeds so slow that it's very unlikely. For the substrates, here we have different types of substrates. So let's first look at the primary. This carbon would be a primary because it's only connected to one other carbon, hence it having the 3 hydrogens. This one would be a secondary. It's connected to 2 carbons. This carbon is connected to carbon 1 and carbon 2. Has 2 hydrogens to make 4 bonds. And this one would be tertiary, connected to 3 hydrogens. 1, 2, and 3. So as a general rule, when you're looking at stability, tertiary is going to be better than secondary, better than primary. It's going to be faster than this one, faster than this one. Okay. So for an example, for the Sn2, we have this molecule, and we're reacting it with NaCl. And notice how this carbon that the leaving group leaves from has 1 carbon attached, 2 carbon attached, 3. So it's tertiary, which is not ideal for Sn2, but just for demonstration purposes, we're going to act like it can undergo. So this is one step. So all at once, the bromine would leave and this would become an electrophilic carbon, and then the non-bonding electrons from the nucleophile, which would be chlorine, would go and attack this electrophile. That would give you a product where chlorine is substituted in place of the bromine. And as I mentioned before, we have inversion of stereochemistry. So since bromine was on a hatch here, the chlorine is now on a wedge. Since the methyl was on a wedge, it is now on a hatch. Just to point out that we're using a regular arrow, which would mean 2 electrons being moved. Compare it to the fish hook, where it's one side of the arrow, that would mean 1 electron is being moved. Okay, that's it for Sn2. So for Sn1 reaction mechanism, it's a 2-step mechanism. And the big idea about this one is that we have a carbocation intermediate. So it's not all happening at once, it's happening in 2 different steps. So the rate law for the Sn1 reaction, as you can see, the rate is only dependent on the concentration of the electrophile. Therefore, any nucleophile will work. You also need a good leaving group. That's true for all substitution reactions. And an Sn1 is sped up by a protic solvent. For our product, we're going to have the racemization, which basically means a mixture of stereochemistry in our products. And the substrate for this one would be, we favor benzylic and allylic, of course, before tertiary, but for this purpose, we're going to go and say tertiary is the best, then secondary, and on a primary, it would proceed so slow that it's very unlikely. Okay, so we have this example with the same molecule being reacted with water. So first the bromine is going to leave, and after the bromine leaves, that's going to leave this carbon missing a bond, so it would be positive. The positive carbon is another word for carbocation. So once we have this carbocation, we notice it's on this carbon, which has 1, 2, 3 carbons attached to it, making it tertiary. Now, for Sn1, it can undergo carbocation rearrangement if necessary. Say, if it was on a secondary, we could do a 1,2-methyl shift or a 1,2-hydride shift to turn it into a tertiary, if possible. But since we're already at the best, which is a tertiary, we don't need to do that. So after we have our carbocation, we have the non-bonding electrons from the water are going to go attack this electrophilic carbon, and we are going to get these 2 products. So as I said before, we had racemization of stereochemistry. So we have 2 different products. On this product, the methyl stayed at a wedge and the OH would stay on a hatch, and this one is switched. The methyl was on a wedge and now it's on a hatch, and this was on a hatch and now it's on a wedge. And for as where the other hydrogen went in the water, it reacted with the bromine floating in solution to make HBr. Okay, that's it for substitution reactions. So now we're going to cover the elimination reaction. So for an elimination reaction, we basically have an alkane and we have an X over here. And at the end of reaction, this X is going to be eliminated to give us a double bond. So this would become an alkene. So our E1 and E2 reactions, our elimination reactions, have a base, a leaving group, and a double bond, which gives us an alkene. And as a general rule for eliminations, we want tertiary before secondary, and primary doesn't really work well with elimination reactions. Okay. So first, looking at our E1 mechanism, it's kind of similar to the Sn1 in that it's a 2-step. The rate is only affected by the concentration of the alkyl halide, the starting material. Okay, and like Sn1, we have a carbocation intermediate. So, as you can see, we'll get to that. Okay, you need a strong base. So with elimination reactions, instead of a nucleophile, we have a base that's going to come in and react to give us that double bond. For E1, there is carbocation rearrangement if necessary, similar to the Sn1. But let's just get into an example. So we have the same molecule, and we're going to react it with methanol and heat to have it undergo an E1 reaction. So as I mentioned before, this is 2 steps, and we're going to need a carbocation intermediate. So the bromine is going to leave, and then we're going to have this carbocation. And let's take note that this carbon is connected to 1, 2, 3 carbons, making it a tertiary. That's good for elimination. Okay, so when we're doing an elimination, we want to look 1 carbon away from where the leaving group left. So if the leaving group left from here, we're going to look at this carbon and this carbon. As you can notice, we have a secondary carbon over here and a tertiary one over here. That's where the Zaitsev rule comes in. So for E1 reactions, we're always going to follow the Zaitsev rule. And what that is that the alkene that forms in an elimination is the most stable one, aka the most substituted. So here we have this one, which has no carbon substituents, which is weaker than this one that has 1 monosubstituted. This one's even stronger. It has 2 R groups, so it's disubstituted. 3, which is even stronger, and if they're all substituents, that is the strongest. So when we're looking at which hydrogen to steal, here we have a secondary carbon. So if we stole one of these hydrogens, the double bond would be here. We would have H, so it wouldn't be fully substituted. But if we took this hydrogen, we wouldn't, all of the sides of the double bond would have a carbon substituent. So by taking this hydrogen and putting the double bond here, we're going to make our Zaitsev product, which is the most stable. So after we have our carbocation, our base, which is the methanol, the non-bonding electrons are going to steal this hydrogen, and then the non-bonding the electrons that were bonding the hydrogen to the molecule are going to contribute to this bond, making our double bond. And this is what our Zaitsev product is going to look like. Okay, moving on to the E2 reaction. For this one, it's kind of similar to Sn2, as in there's no carbocation intermediate. And the difference in this one is it can make the Hofmann product. Let's go back to here for a second. If we were to take a hydrogen from here and make a product, even though this one's more stable, so the lesser stable product is the Hofmann product. And that can be done in an E2 reaction if we use a bulky base. Because a bulky base doesn't have anywhere to go. In this, it's you have a carbon here, you have another carbon here. It's too crowded, and the bulky base wouldn't be able to get in there. So it has no choice but to go to the other side. And we're going to see that in a second. So this one is 1 step. So we have the bromine leaving. We have the non-bonding electrons reacting with stealing the hydrogen. Sorry, I forgot to mention. In an E2 reaction, the base must attack the hydrogen that's anti-periplanar. And basically what that means is that it's farthest away from the leaving group. So here we have a very bulky base. And as you can see, bromine is our leaving group. So the bromine is going to leave. And we have 2 hydrogens that it can steal from. So as we said, we want it to be anti-periplanar. So since the bromine is going away from us, we're going to want to take from the hydrogen that is coming to us. So that means the non-bonding electron from here is going to steal this hydrogen, and then the electrons that were bonding the hydrogen are going to contribute to the double bond. That's going to give you this Hofmann product. Okay, next we'll get into some examples. Okay, so for our example problems, we just want to keep in mind that for the substitution reactions, we want a good nucleophile. For the elimination reactions, we want a good base. So Here we have our molecule, and we have methoxide that we're reacting it, which is a strong base and a strong nucleophile. So both substitution and elimination are in the picture. And for our substrate, the carbon that the leaving group is attached to is a secondary because it's attached to 1, 2 carbons. Okay. Wait, where is it? No, it's a secondary. Okay. So when we have both a strong base and strong nucleophile on a secondary, we see that Sn2 and E2 are possible, but E2 is going to proceed faster in this case. So we're going to do the reaction as if it were an E2, an elimination. So E2, as we know, was one step, so the chlorine is going to leave, and then our base is going to attack the hydrogen that is antiperiplanar, and we know it's going to take from a hydrogen over here because that would give us a more stable product going back to the Zaitsev rule. So since we want antiperiplanar, the chlorine's on a wedge, we're going to want to take a hydrogen that's on a hatch. So the base is going to attack that hydrogen, and the electrons that we're bonding the hydrogen to the molecule is going to contribute to our newly double bond, which will give you this product, which would be our Zaitsev product. Okay. Now for number 2, we have basically the same thing, but instead we have DBU and OTOS as our leaving group. Once again, it's a secondary. This carbon is connected to 1, 2 carbons. Our DBU is a bad nucleophile, but it is a strong base. Bad nucleophile, so we can rule out substitution, and it's a strong base. So that means it can be E1 or E2. So when we have a weak nucleophile and a strong base on a secondary, that's going to give us our E2 reaction. So we have E2. So E2 is one step, and we need antiperiplanar. So our leaving group is going to leave. It's going not to attack. There's 3 hydrogens over here. It's not going to take those because that would be our Hoffman product. Instead, it's going to take the hydrogen over here. That's also antiperiplanar, and that would give us our Zaitsev product. So the electrons from our DBU are going to attack this hydrogen, and then the electrons that were bonding the hydrogen are going to go here towards our double bond to give us this product. Okay, under an E2. Okay, so number 3, we again have chlorine as our leaving group, and then ethanol, which is a protic solvent, and then ethoxide, which is a good nucleophile, strong base. And the carbon that is our leaving group is attached to is connected to 1, 2 carbons. So that would give us a secondary. So similar to what we did in number 1, that would give us an E2 reaction because even though we have a good nucleophile, E2 proceeds faster than Sn2. So once again, we're going to do an E2 reaction where our chlorine is going to leave, and then our electrons are either going to steal we're going to look 1 carbon away, so we can steal a hydrogen from here, which is on a wedge, or one of these hydrogens. And going back to our Zaitsev rule, we know that it's going to take the hydrogen from here because it checks our boxes for antiperiplanar, and it would give us a more stable, more substituted product. So our base is going to take this hydrogen, and the hydrogen that, the electrons that were attaching the hydrogen to the molecule are going to contribute to the double bond to give us, right here, where the chlorine is eliminated and we still have this methyl, which is now not going away or coming towards us because we have a double bond here, sp2. There is no, it's flat, so there's nothing coming towards us or going away from us. Okay, so again, we have starting material where chlorine is the leaving group. We have ethoxide, which is a strong base and a good nucleophile, and we have a secondary substrate, which is the same as the other one. So we know that this is going to proceed under an E2 reaction. But the difference is that our methyl this time is on a wedge, meaning our hydrogen is on a hatch. And we know that for E2, we need something that's anti-periplanar to the leaving group. So since the leaving group is on a hatch, we need a hydrogen that is on a wedge. And over here, there's no hydrogen for us to take that's on a wedge. That means we have to look over to this carbon, and our base is actually going to attack this hydrogen over here. So we have our ethoxide, and the non-bonding electrons for the base are going to attack this hydrogen, and these electrons are going to contribute to a double bond that is right over here, which would give us this product. We still have our methyl that is on a wedge because we didn't do anything to this side. And our chlorine is gone, and we have a double bond right here with our now flat ethyl. This is an ethyl, by the way. Okay. That's that for that. Okay, number 5. We have bromine as our leaving group and DMF as an aprotic solvent. And then we have acetate. Acetate is a strong nucleophile and a weak base. Since we have a weak base, we can't do an elimination. So it's going to have to be substitution. When we have a strong nucleophile and a weak base on a secondary, Sn2 if aprotic, Sn1 if protic. And we see that we have DMF as an aprotic. So that means we are going to have an Sn2. As we know, Sn2 is one step, so we're going to have our bromine leave, and then we're going to have the electrons from the negative oxygen attack the electrophile to give us a product where the acetate replaces the bromine. And we should also remember that for this, oh, I forgot to add the methyl. There's supposed to be methyl there, sorry. We also know for this, for Sn2, we have inversion of stereochemistry. So since our bromine was on a wedge, our acetate is going to be on a hatch. We can just draw it in like so. Okay, so that is that one all done. Number 6. We have N3, which is a strong nucleophile and a weak base. And our leaving group, which would be this oxygen right here, we would have, it's on a carbon that's only attached to one other carbon, making it a primary. So for a strong nucleophile, weak base, we have a weak base, so we can't do eliminations. And when we have a primary, it can't undergo Sn1, so we're going to do Sn2. So another substitution. We know it's one step. Our leaving group is going to leave. In solution, the N3 is going to separate from the lithium. And then our nucleophile is going to attack the electrophilic carbon all at once to give us a product that looks like this. Okay. Number 7 and 8, we have reacting with NaH, so we have hydride once it separates from sodium in solution, which is a weak nucleophile but a strong base. And our leaving group would be the bromine. It's a better leaving group than the OH because it's bigger. That means it's a weaker base, which, as we know, weak bases make good leaving groups. So bromine is going to be our leaving group. The carbon that the bromine's attached to is attached to 2 carbons, making it secondary. We have a weak nucleophile, so we cannot do a substitution, but we have a strong base, so we can do an elimination. So weak nucleophile, strong base on a secondary, we know that's E2. So this is going to proceed under an E2 mechanism. We know that E2 is 1 step, so we have our hydrogen, our bromine is going to leave, and then our hydrogen can attack, our base can attack a hydrogen from here or here. And as we know, for an E2, we need anti-periplanar. So since the bromine is on a wedge, it's going to need a hydrogen on a hatch. So let's draw in our hydrogens. And according to Zaitsev rule, we know that we're going to take this hydrogen because a double bond here would give us a more substituted product, which would be Zaitsev. So once you do that, the bromine leaves, the base attacks this hydrogen, and these electrons are going to contribute to a double bond right here to give us here and a flat OH because it's sp2. Now for number 8, we have the same thing, but so we know it's an E2, but oxygen, the OH is on a hatch this time, meaning our hydrogen over here would be on a wedge. We have this on a wedge and on a hatch. As we know, our leaving group is going to leave. Our leaving group is on a wedge, so we need a hydrogen on a hatch. Now on this carbon, even though there's this OH here, there's no hydrogen on a hatch. So we're forced to take this hydrogen over here that's on a hatch. So our base is going to attack the hydrogen, and then the electrons that were attaching the hydrogen to the molecule are going to contribute to a double bond on this side, which would give us a product that looks like our OH is the same, and then would give us a product that looks like this. Okay, and that's it for Sn1, Sn2, E1, and E2 reactions.